So in the previous lecture, we have seen what is the direct product, and we calculated the direct product of various irreducible representations. So in this lecture, we will be looking at how direct product is used to solve quantum mechanical problems of quantum mechanics. So direct product applications. So let us start with what we know. So we know what is an even function and what is an odd function, right? So let us suppose that fx is an even function. And if it is so, then assuming that it is continuous over all range, the integration of fx will not be equal to 0 because it's an even function. Whereas if fx is an odd function, then the integration of fx dx will be equal to 0, right? So we can see this example as cos x. So cos x dx over all space will not be equal to 0, whereas sin x dx over all space will be equal to 0. So why is it so? Because let's draw this function to understand it more clearly. So if we draw the cosine function, it goes like this, right? And then on the other side, it goes like this. So assuming this is my x-axis and this is my y-axis. So that means if I am putting a plane which is YZ plane, so sigma YZ if I'm putting, then if I operate sigma YZ onto the cos x, I will get cos x, right? That means the character under this is +1, right? So this would imply that cos x is invariant under sigma yz. Okay, so this tells us that invariant because our character is +1 when we apply sigma yz onto cos x, right? So now we understood how we apply various symmetry operations. We can onto different molecules. So similarly, we can apply this symmetry operation onto a mathematical function as well. So whereas if you apply sigma yz onto sin x, you will not get +1 as the character, right? So now let us think that you have a integration to solve where you have two functions fa fb. You don't know whether it is even and odd or the product of that is even or odd. It is sometimes not easy or straightforward to calculate, but we can see how in context of symmetry and group theory we can solve this integration, or we can at least tell whether it is going to be 0 or non-zero. So let's say if this integrand fa fb, so let's call this integrand, the product of fa and fb is invariant under all the symmetry operations a molecule has. So we are talking about a molecule and the corresponding symmetry operations. So whenever we are considering a molecule, then it has certain symmetry operations and then it falls under a particular point group. So in that context, if two functions which form basis of certain representations, so they are invariant under all the symmetry operations a molecule has, then let's call this as I, then the integration will not be equal to 0. That means it is behaving as even function, just like we saw the case of cosine x, right? So just like we saw the case here, cos x dx. So because it is invariant under sigma yz, we saw that it is not equal to 0. Similarly, the integrand is invariant under all the symmetry operations. Here the symmetry operation we chose was only sigma yz, but here we are saying that if the integration is invariant under all the symmetry operations, then I will not be equal to 0. Otherwise, if it is variant, that means if it changes by application of a symmetry operation, then the integration will straight away go to 0. So it is a very useful thing in quantum mechanical problems, whether a integration will be equal to 0, will vanish or will not vanish. So we will see that. Let's see. So what does it imply? This means that, so if this product FAFB forms basis of a totally symmetric representation. So we know what a totally symmetric representation is. It carries 1 under all the symmetry operations. So if FAFB, the product of this or the integrand here, forms the basis of a totally symmetric representation, that would mean that it is invariant under all the symmetry operations, and then the integrand or the I will not be equal to 0. So, or let's say if FAFB forms basis of a reducible representation, right? It is possible that it can form basis for a irreducible or a reducible representation. We don't know. So let's say if it forms the basis of a reducible representation, then at least one of the component IRs or IR representations must be totally symmetric representation. And in that case, I will not be equal to 0. Right? So either it should form the basis for a totally symmetric representation, or it should form the basis of a reducible representation, which in turn should contain at least one IR representation. Okay, so when would that be? So let's say if FA forms the basis of tau A and FB forms the basis of tau B, right? So in that case, the matrix representation for FAFB will be given by tau A direct product tau B, right? And tau A tau B direct product will have totally symmetric representation TSR only when A is equal to B and will never contain a TSR when A is not equal to B, right? So that means direct product of a IR representation with itself will contain totally symmetric representation. So that means FA and FB should form or must form the basis for same IR representation. Then only the integration will survive, otherwise the integration will go to 0. So for example, in the case of C4V, when we calculated a direct product of E cross E, we saw that it can be reduced to A1 plus A2 plus B1 plus B2. So that would mean that my if FA forms the basis of E and FB forms the basis for E in this particular case, then I will not be equal to 0. Otherwise, if FA and FB are forming basis for two different representations, then I will be equal to 0. So the problem is now very simplified. All we have to do is, given a function, we have to find out what is the irreducible representation to which that particular function is forming the basis of, right? If the two functions are forming basis for a same representation, the I will not be equal to 0. If the two functions are forming basis for two different representations, I will be equal to 0, right? So very simple now. So now let's also look at, in the same way, let's also look at integration of triple product, whether it will be equal to 0 or not. So this will not be equal to 0 when direct product of the representations tau A, tau B and tau C, assuming that FA is corresponding to tau A, FB is corresponding to tau B and FC is corresponding to tau C, must be or contain the totally symmetric representation, right? So either they form a totally symmetric representation or they must contain totally symmetric representation at least once. And when is this possible? This is possible only if representations of the direct product of any two of these is or contain the same representation as given by the third function. So let's try to digest this. So what we are saying is that if there are three IR representations corresponding to these three functions, then the direct product of all three must contain totally symmetric representation. So this is possible if if the representation of the direct product of any two of these functions, let's say tau A into tau B, must contain tau C, right? Or tau B into tau C must contain tau A, and so on. So let us see how it works. So let's say if we have FA is the basis for tau A, FB is the basis for tau B, and FC is the basis for tau C, and we have what we are trying to calculate is direct product of tau A and tau B, that may contain A1 times tau C plus A2 times tau I plus A3 times tau J and so on. So now then if we calculate the triple direct product now, tau B, tau C, then this will be A1 tau C plus A2 tau I plus A3 tau J, direct product tau C. Now if you see A1 tau C, direct product tau C plus A2 tau I tau C and so on. So this is the only one which will give you A1, or let's call it as TSR, totally symmetric representation. None of the other direct products, because they are direct products between two different IR representations, they will never give A1. That is the totally symmetric representation. So you will get totally symmetric representation only from direct product of tau c into tau c. So that means tau A into tau B must contain tau C, right? So only if tau A into tau B contains tau C, then we have A1 present in the system. And if we have A1 present in the system, we can say that the integration of FA, FB, FC is invariant under all symmetry operations. If it is invariant, it behaves like an even function and the integration is not equal to 0, right? So that is the point what we are trying to make. So let's say now let's try to see where this particular integration is useful. So in energy of a particle, in calculating energy of a particle or energy between two states and so on. So let's say in quantum mechanics, we often come across with the integral where we have to calculate energy of a particle. Like, how do we do that? So we know this equation, h psi equal to E psi, and what we can do is we can multiply, we can write this thing equation, write it like this. Let's say this is star and psi j star psi I, this will be equal to A, right? So now this is the energy of the interaction between the states psi I, psi j and psi I, right? So now how to solve this integration now? So let's say, so now we have to estimate or rather calculate what is the IR representation to which psi j, h and psi I are forming the basis, right? So let's first talk about h. So we know that h is Hamiltonian, right? So we know that h is invariant under all symmetry operations. We have seen that earlier, right? All symmetry operations. So we have seen that H and R commute with each other, right? That means it will not matter whether we are first operating the symmetry operation or first doing the energy estimation. This would mean that H will remain invariant under all the symmetry operations. That means H will form the basis of totally symmetric representation, right? So that means now if we know tau j and tau I, then this does not actually matter because this is always tau A. A is the totally symmetric representation, right? So this would imply that if psi I and psi j belong to same IR representation, only then totally symmetric representation can occur in this product. So to know whether this integration will go to 0 or not, we need to identify whether these two will form basis of same IR representation or not. If they form basis of same IR representation, then TSR will exist in this product. If TSR will exist, the integration will be non-zero. So that means there would be finite energy. Otherwise, the integration will be equal to 0 if these two form basis of two different IR representations. And then we can say that the energy of interaction between the two states is 0, right? So this whole, if numerator goes to 0, the whole thing goes to 0. All right. Okay. So So that is it. So we can estimate the energy of the particle. So let us do a quick, or let me give you a quick assignment. Let's do a home assignment to see if you can follow this. Otherwise, we can always discuss in the interaction session. So let's say if I want you to evaluate psi lambda star, let's say AP and phi v. So this is a bracket notation. Basically, it means the same thing the way it is written over here, but let's not worry about. So this is another form you may get questions in different books. So that's why I'm using this notation over here. So where psi lambda belongs to E1U and AP belongs to B2G and phi V belongs to B1G of B6H point. So the three representations are given. So psi lambda is E1U, AP is B2G, and phi V is B1G. So what you have to do is now you have to take the direct product of all three and see whether, and then try to use the reduction formula to see whether there is A1 present or not. If A1 is present, or A1G, whatever will be the totally symmetric representation in this case, if it is present, then it will be equal to 0, otherwise it will not be equal to 0. So all you have to do is you have to tell whether this integration will survive. That means will not be equal to 0 or will be equal to 0. Okay. So in next class, we'll see one more application of direct product, and then we'll shift gears and we'll look into symmetry adapted linear combinations. So we'll see one more, we'll spend some more time on direct product for one more class. Go to next topic after that. All right. Thank you.